Okay, continue to the next section, which is the partial fraction. Okay, so this partial fraction allows us to integrate any rational function by expressing it as a sum of simpler fraction, i.e. the partial fraction. So you compare this in this example. So you look at this left-hand side here, 2 over x minus 1 minus 1 over x plus 2. If you combine these fractions together, you'll get the one as you see on the right hand side. So if you are asked to integrate the right hand side here, it would be easier if you can break it down to this kind of function. So you can integrate them separately. Okay, so you want to convert from this right hand side here, this fraction, into partial fraction. You want to divide them into two separate simpler functions so that you can integrate them separately. Okay, just shown in this example here. Okay, x plus 5 over x squared plus x minus 2, which is this one. So this one is actually equal to the one here. Then you can integrate them separately, and it's much easier that way. So in order to do that, we need to know how to convert to partial fraction. So let's say if you have a function fx given as a polynomial fraction, okay, p as a function of x and q as a function of x, px and qx are polynomials. So you want to express the function of f as a sum of simpler functions where the degree of p is less than the degree of q, i.e. you want to have a proper fraction. So what does it mean by the degree of the polynomial? And when would the function fx be improper? Okay, so if you look at your notes, you can identify the degree of the polynomial by just looking at the highest power or highest degree of the variable inside the polynomial. So if you have a function of x to the power of 4 plus something x to the power of 3 and so on, you look at the highest degree of the highest power of the x, then that will give you the degree of the polynomial. So when would the function fx be improper? The function fx is an improper function when the degree of p is greater than the degree of q. You know, like the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator. So we need to convert it into a proper function. So how do we convert it into partial fraction first? So we need to use the technique of long division until a remainder r is obtained such that the degree of r, the polynomial r, is less than the degree of the denominator qx. Okay, so we can write down the division statement as given here. So given a function f of x equals to the fraction p divided by q, so if you break down this p over q by long division, you shall get a polynomial s plus the polynomial r divided by the original denominator. So we shall do that in the next example. Right, so you can see this example 4 here. You want to convert the partial fraction in order to be able to integrate it. Okay, so if you want to integrate this function, so x to the power of 3 plus x divided by x minus 1 with respect to x. So these are the steps that you can see based on your book. So you just look at the numerator. It has a greater degree than the denominator. It should be denominator here, okay? Thus, you need to do long division to make it a proper function. Then, perform the long division until a remainder is obtained where the degree is smaller than the denominator. Then, write the integral function in terms of partial fraction, and finally, do the integration. So, why don't you pause and try to do the long division and finally do the actual integration. Okay, so let's do the solution together. Let's do the long division first. So you have this as the denominator, x3 plus, alright, so although there is no x squared term, so I'd like to leave it empty so that it does not confuse me when I do the long division. You may have a different way, but this is how I do it. Okay, so this one you want to divide by x minus 1. So x to the power of 3, you shall get x squared here. So x squared times x, you get x cubed. Then x squared times minus 1, you get minus x squared. Then you want to minus everything here. So x cubed minus x cubed is 0, and 0 x squared here minus minus 1 is just x squared, and then you bring this down plus x, then you divide again, okay, plus x. So then you shall get x squared when you multiply back, okay. Then you get here x squared minus x squared is 0, x minus minus x is 2x, okay. So then this 2x you still want to divide, okay, plus 2, so 2 times x is 2x, and here is 0, right? So just follow on. Then 2x times 2 times minus 1 is minus 1, okay. So this one, everything is minus, so you get, no, sorry, 2 times 1 is 2 instead of 1. So here you have 2, okay. Okay. So x cubed plus x over x minus 1 actually is equal to x squared plus x plus 2 plus 2 over x minus 1. So when you want to integrate this function with respect to x, you can integrate the same thing with respect to x on the right hand side. So you can see that it's easier to integrate the terms on the right hand side compared to when you don't convert it into partial fraction, right? So let's do the integration. So you get x cubed over 3 plus x squared over 2 plus 2x plus 2 ln x minus 1 plus integration constant, because this is an indefinite integral, right? Okay, when we want to convert the partial fraction, convert to partial fraction, so let's say we are given this function, okay? So if you have the denominator q of x is a more complicated version, it needs to be factored as far as possible. You want to factorize it as simple as possible. For example, if you're given qx equal to x to the power of 4 minus 16, so you can factor this polynomial into this, okay, x squared minus 4 times x squared plus 4. Also from here, from this x squared minus 4, if you recognize, you can further factorize it into x minus 2 times x plus 2. Okay, so this would be the most simplified version of the polynomial q here. Then the proper rational function of r over q can be expressed as a sum of partial fractions in the following form. So we will see the different cases of converting to partial fraction in the next slide. Okay, so these are the 4 cases when you want to convert to partial fraction. So you need to identify, look at the denominator q. The first case is when the denominator q is a product of distinct linear factors. So we have, for this each case here, for the 4 cases here, we have different methods of converting them into partial fraction. Okay, so I mean the key is to identify the characteristic of the denominator q. So just look at all these 4 cases. We will go through one by one with examples in the following slides, okay? So for case number 1, where the q of x is a product of distinct linear factors, meaning when you factorize the polynomial q of x, you will end up with different linear functions. Okay, in this case, a1x plus b1, a2x plus b2, and so on and so on. Depend how many linear factors you can have when you factorize the q. Okay, no factor is repeated and no factor is a constant multiple of another. So these are all the distinct linear factors. Okay, so if you have q, when you broke it down in like this, you have something like this. So you can break down the partial fraction in terms of this. R over q equals to a1 over the first linear term plus a2 over the second linear term, and so on until you reach the final linear term. Okay, so a1, a2 until ak here are just coefficients. Okay, so let's do example 5 to convert into partial fraction for case number 1. So let's say you want to evaluate the integral of this fraction here. So since the degree of numerator is already less than the degree of denominator, you don't want to divide already. I mean, it's already a proper function, but we want to simplify this function into separate fractions. Still we want to make it into a partial fraction. So we want to factor the denominator first, and then we write the numerator in terms of constant, and we find the value of the constant from the system of equations, and then substitute the value, then only we integrate. Okay, let's do that. Okay, so for the given question, you have, why is the default always red? Okay, you have this integral x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x with respect to x. So first of all, factor the denominator, factorize the q of x. Okay, so you want to simplify this. Okay, take out the x, and then got this. So this one you can factorize into, now this is just a quadratic equation, so you can factorize to x, and then 2 and 1, and then plus, yeah, I'm doing manually. Okay, 2x minus 1, x plus 2. Okay, so then next step is to write the numerator in terms of constant. So since this is the first case, you can see that there are three distinct linear factors. So this is one linear factor, second, and two, none of which are repeated. So you can write down these x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x equal to the first constant, a over x, plus the second constant, b over 2x minus 1, plus the third constant, c over x plus 2. Okay, so now the next step is to determine the constants of a, b, and c. So let's do that. So how do we want to determine the constant? We want to set a system of equations, because you know this numerator, then it should be all the same with the numerator. So you know how to get to the common numerator, right? So a needs to be multiplied by 2x minus 1 and x plus 2, plus b needs to be multiplied by x and x plus 2, plus c needs to be multiplied by x and 2x minus 1. That would be the same equal to x squared plus 2x minus 1. So you solve this system of equation to find out what are the values of a, b, and c. Okay, so just follow. Oops. Okay, so you can collect all the terms together. Let's say for x squared, you have 2a plus b plus 2c equals to 1. And then for x, you have 3a plus 2b minus c equal to 2. And for 1 or minus 1, you have minus 2a equal to minus 1. So here you have the sets of equations where this is equation 1, equation 2, equation 3. So you have three equations with three unknowns. I'm sure you've heard this before. Thus you have enough information to solve for a, b, and c. Okay, so let's start with equation 3 first, because that's the most obvious. So from 3 you get a equals to 1 over 2. Then from here you can substitute the values of a equals 1 over 2 into equations 1 and 2 and solve for b and c. So I'll let you do that on your own and just give you the final answer, or you already have the final answer in your notes actually. So b is 1 over 5 and c is negative 1 over 10. Okay, so your partial fraction is now, so original fraction is you have this, okay? Okay, so you have a over x plus b over 2x minus 1 plus c over x plus 2, and we have found out the values of a, b, and c earlier. So a is 1 over 2, so you put 1 over 2x here. So b is 1 over 5, so you have 1 over 5 times 2x minus 1, and c is minus 110, so you get minus here and 1 over 10. So when you want to integrate this with respect to x, then you can integrate separately all this partial fraction with respect to x. Okay, so I think you can do that easily now. Right, okay, so you can integrate them separately. So 1 over 2x dx plus integral of 1 over 5 2x minus 1 dx minus integral of 1 over 10 x plus 2 dx. So the first two terms here, the first term and the third term, it's quite straightforward, but the middle term you need to use a u substitution. So let's do the first and third term, which are straightforward first. So integrate 1 over 2x, you will get 1 over 2 ln of x. Okay, let's leave the middle term for a while now. And then the third term, you just also integrate straightforward. And then don't forget to plus the constant. However, the second term here, you need to do the u substitution. So let's let u equal to 2x minus 1. So thus du equals to 2 dx. Thus dx equals to du over 2. So when you want to integrate that 1 over 5 2x minus 1 dx, it's the same with integrating 1 over 5 u du over 2, and you get 1 over 10 ln u, and then you put it back in terms of x, 1 over 10 ln of 2x minus 1, then you put it back inside the middle equation here, 1 over 10 ln of 2x minus 1. Okay, yeah, that's it. This is your final answer. Okay. Right, so moving on to the second case of partial fraction, where qx is a product of distinct linear factors, some of which are repeated. Okay, in this case, you have qx, where when you factorize, it's a repeated linear factor. The linear factor, the same linear factor is repeated r number of times. Okay, thus the rational function of r over q becomes first constant a1 divided by the first linear factor to the power of 1 plus a2, the second constant, divided by the linear factor to the power of 2, and you repeat until r number of times the linear factor is being repeated. We'll do an example to clarify how this works. Okay, example 6, converting to partial fraction for case number 2. Okay, you're given this integral, you want to integrate this function, so you look at the numerator, it has a higher degree than the denominator, so you need to divide using long division to make it into a proper fraction first, and then you want to factor out the denominator to see what are the linear factors and how many times is it being repeated, and then find the constant so that you can finalize your partial fraction and finally integrate the actual function. Okay, so let's do the first step where we do the long division. So write down x to the power of 4. We don't have x cubed, but I'm going to leave it empty there so as not to mix up my long division. So then 2 minus x, minus 2x squared plus 4x plus 1 divide by the denominator x cubed minus x squared minus x plus 1. So let's do it. So x here, so you get x4, so x times x here you get minus x cubed, x times x you get minus x squared, and the x times 1 plus x. Then this one you minus everything, so here you get x cubed, and then minus 2 minus minus 1 you get minus 1 x squared. 4 minus 1 is plus 3x, and then bring the 1 down, then continue the process. X cubed divided by x cubed, you get you get 1. Okay, so 1 times x cubed is x cubed, 1 times x squared is x minus x squared, 1 times minus x is minus x, 1 times 1 is 1. Then minus everything here, so you get 4x. So your partial fraction has now become x plus 1 plus 4x over x cubed minus x squared minus x plus 1. So this is your simplified partial fraction. So this is your Rx plus Px over Qx. And if you notice, your Qx here is, you can factorize into some distinct linear factors, some of which are repeated. Okay, so let's do the factorization here. Okay, so this x cubed minus x squared minus x plus 1, you can factorize it, factorize the cubic polynomial. So maybe you have seen this before in your pre-university. Okay, so I'm just breaking down this term and this term so that I can get some quadratic function which I can maybe break down further or not. I just want to find a common factor for this cubic polynomial. So here we're just factoring portion by portion. Okay, so we're factoring this one x squared and the x plus 1, and then we want to factor this maybe 2x times x plus 1, and then I'm sorry, this one should be plus, right? Okay, then get x plus 1. So if you notice here, a common factor is the x plus 1. Okay, so we can take that x plus 1 out and then factorize the whole thing. Then x squared minus 2x plus 1. Okay, so this one is one linear function which you don't need to factorize anymore, but the quadratic part here, you need to factorize it further. So you factorize the quadratic equation, so you get this is just the x plus 1, just take it down, and then this one you can write it down as x minus 1 and x minus 1, which is actually x plus 1 and x minus 1 square. Okay, so you have factorized your qx into some linear function, some of which is repeated. So in this case, the repeated linear function is this x minus 1. Okay, after we have factorized just now, so we can write down this part of the partial fraction x3 minus x squared minus, okay, to be equal to 4x over x plus x minus 1 squared times x plus 1. So since this is a case 2 where after we factorize the denominator, we have the linear function, some of which are repeated. So in this case, the x minus 1 is the one that is repeated. So we want to write that down as a over x minus 1 plus the second coefficient b over x minus 1 squared plus the third coefficient c, x plus 1. Okay, so now we want to find out what are the values of a, b, and c. So we just figure out a system of equation. So you can skip this if you don't want to see, but I'm just going to proceed to do it. Okay, this equal to 4x. So yeah, you can further simplify it. A times x squared minus 1 plus b x plus 1 plus c. Then you expand this part of the equation, the expression. Okay, so you get x squared minus a plus bx plus b plus cx squared minus 2cx plus c equals to 4x. Then for x squared, it's actually equal to 0. The coefficients are a and c. So a plus c equals 0, that one equation. So for x, coefficient is equals to 4. And for x is b and 2c. b minus 2c equals to 4. And for 0, it's actually equals to 0. This one, and this one. So minus a plus b plus c equals to 0. So here you can solve the system of equation. You have 1, 2, 3 equations, 3 unknown. Solve for a, b, and c. So you get a equals to 1, b equals to 2, and c equals to minus 1. So you can just replace these values into this value to get what is your partial fraction lah. So coming back to our original given equation, so from here we have broken this down to after long division we get this x plus 1 plus 4x over x cubed minus x squared minus x plus 1, and this part here we have broken it down into the ABC. So let's just follow through. Okay, so we just follow through that. The A is 1 just now. Okay, 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1 dx. So from this we have simplified. After we have converted it into partial fraction, we have to get to this expression, so we can integrate with respect to x much easily. So we just integrate x squared over 2 term by term. Okay, so integrate 1, you got x. Integrate 1 over x minus 1, you got ln of x minus 1, and then you integrate this term here, you get minus 2 over x minus 1, and this one you get ln over x plus 1 plus the integration constant. Then you can simplify the terms with the ln. Okay, I just collecting the terms together, plus ln of x minus 1 over x plus 1 plus c. Yeah, that's it really. So this is your final solution, right? So from the original given long fraction here that you want to integrate, first you get it into the partial fraction, and then you further simplify the denominator into distinct linear functions, some of which are repeated, and then you integrate. Okay, for case number 3, where we have the qx as an irreducible quadratic factors, none of which is repeated, so we cannot factorize the qx into some linear functions. So whenever we cannot factorize, usually it's because if you have this qx in terms of ax squared plus bx plus c, then you look at the discriminant b squared minus 4ac less than 0. The value is less than 0. So in this case, the rational function of r over q will have a term of the form like this. So it's a linear function as the numerator divided by the irreducible quadratic factor of the denominator. Okay, so if you have something like this, you can integrate by completing the square if necessary and using the following formula. You have to convert the fraction into something that looks like this, so that you can use this formula. If you have this, for example, 1 over x squared plus a squared, integrate with respect to x, you can use this formula straight away. So we want to convert those into this form. Okay, so in this example, evaluate this integration of this fraction. So in this case, if you look at the numerator, it has the same degree with the denominator. So is it a proper or improper fraction? So in this case, although the degree are the same, it's considered an improper fraction. So we need to do long division to get into a proper function. And then we want to check the value of the discriminant of the denominator, to check the value of b squared minus 4ac. Okay, then we do completing the square if necessary. Then we use the u substitution as a function of x to facilitate the integration. And we want to convert everything in terms of this formula so that we can use this to solve the integration. Okay, do the long division. 4x squared minus 3x plus 2 divide by the denominator 4x squared minus 4x plus 3. So you have 1 here. Okay, minus everything, you have x minus 1. So you can write that down, this one, original function here, to be equal to 1 plus x minus 1 over 4x squared minus 4x plus 3. And then now we want to check this one. What is the value of b squared minus 4ac for this qx here? So b squared minus 4ac equal to negative 4 squared minus 4 times 4 times 3. You get negative 32, which is less than 0, so you cannot easily factorize. Thus, you need to do completing the square. So maybe there are different ways of doing completing the square. But since here we don't have it equal to 0, we cannot manipulate the adding and minusing on the left hand side and the right hand side. So we want to just simply make it in terms of something that we can factorize. Okay, 4x squared minus 4x, and then I'm going to break down this 3 here into 1 plus 2 because this term here, it can be factorized into a quadratic function. So that can be 2x, 2x, and 1 and 1, minus minus, 2x minus 1 and 2x minus 1 plus 2. So this one could be this, yeah, in terms of completing the square. So this thing, you can put it into the original equation. Okay, you want to put this into this, okay, because initially you were asked to integrate this with respect to x, so same thing like you integrate this with respect to x. Okay, so when we put that in, we get integration of 1 plus x minus 1 divided by 2x minus 1 squared plus 2 dx. Okay, so you want to integrate this separately. So you integrate 1 with respect to x, that's easy. Then you integrate this with respect to x. Okay, I think this one is considered done. So integrate 1 with respect to x, you get x. But this is the part here that you need to do some u substitution. So let's do that. Okay, let u equal to 2x minus 1, then du equals to 2 dx, thus dx equals to du over 2. Okay, so here you can have that term as x minus 1 is, from here you can convert the x minus 1, okay? So here you have x equals to u plus 1 over 2, so x minus 1 is u plus 1 over 2 minus 1 equals to u plus 1 minus 2 over 2 is u minus 1 over 2. So you have here 1 over 2, So I screw up the last part of the last slide, so I'm just going to continue because I'm not going to repeat everything again. So yeah, so 1 dx plus integration of x minus 1 over 2x minus 1 squared plus 2 dx. So here we said that we want to let u equal to be 2x minus 1, thus du equals to 2 dx, and dx thus is du over 2. And since we have the numerator here as x minus 1, so from here you can get x equals to u plus 1 over 2. So x minus 1 is u plus 1 over 2 minus 1, which is u plus 1 over okay, so you substitute this both of these part here into this second part. So here let's settle this one first. It's easy. So x plus the integration of, okay, x minus 1 is in this case u minus 1 over 2. Then 2x minus 1 is u squared plus 2, and dx is du over 2. Okay, so you get x plus, so you take out the 1 over 2 and 1 over 2 out, so you get 1 over 4. Then you integrate the u minus 1 over u squared plus 2 du with respect to u. X plus 1 over 4 and integrate u over u2 plus 2 du plus 1 over 4, or just minus here, du over u squared plus 2 du. Okay, or maybe I'll just continue on the next slide because it looks messy. Right, continue. So you can see that on this right hand side here, I have copied from somewhere the integral table. You can Google it, just Google integral table to see some shortcuts on what to do if you have gone to this stage. When you have simplified things, then you can just look at the table. Okay, so here you have to integrate the second part here in the middle here, u squared over u over u squared plus 2 with respect to u. So here you just substitute the x here with u. Everything will be in terms of u then. Then you have this x plus 1 over 4 times 1 over 2 ln your a squared here is your 2, and your x squared is your u squared. So you just put u squared plus 2. And then for this part here, you can use this one, which we intend to simplify this term to just now. So 1 over 4 times 1 over a. So here your a squared is 2. So your a is the square root of 2. And then arctangent of u over a, u over 2, square root of 2. Plus, of course, the integration constant. And finally, don't just stop there. You need to substitute everything back in terms of x, okay? So x plus 1 over 8 ln of, just now our u is 2x minus 1, right? So ln of 2x minus 1 squared plus 2 minus 1 over 4 sec 2 arctangent of u is 2x minus 1 over sec 2 plus c. And this term here is actually the denominator, so you can just put x plus 1 over 8 ln of 4x squared minus 4x plus 3 minus 1 over 4 sec 2 arctangent of 2x minus 1 over sec 2 plus c. Yeah, finally we got to this stage, but it takes a long way. We need to convert the partial fraction into proper and then try to reduce the quadratic into completing the square so that you can reach to the stage here where you can use this formula to finally solve the integration. For case number 4, your denominator qx contains a repeated irreducible quadratic factor. So here qx has the factor of a quadratic, but this time it is repeated. Okay, it's repeated r number of times. So if you have this case, you can reduce the partial fraction in terms of this. So you have the first one, instead of just coefficient, you have the numerator as the linear function. Okay, then you repeat the denominator to r number of times it is being repeated. So each of the term can be integrated using a substitution or by first completing the square if necessary. It depends on the question you are given. Okay, for this example, we want to convert to partial fraction for case number 4. So if you look at this, so you have the degree of polynomial for the numerator is x cubed. And the denominator is actually you have x to the power of 5 if you expand everything here. But what's important here is when you look at the denominator qx, you can see that x squared plus 1 is actually a quadratic function, irreducible quadratic function, which is repeated 2 times. So you can easily identify this as case 4 and try to write down the value of the partial fraction in terms of what we seen earlier in the previous slide. So follow the steps here. So we check the value of the discriminant b squared minus 4ac if you can check on your own, and decompose the function according to case 4 theorem and find the coefficients, and finally do the integration. So why don't you try to pause if you want to try to solve the problem on your own. So in this case, we want to convert the original given fraction into simple one. Okay. So you know that you can convert this into a over x. So I'm just going to remove all these integral terms first. Okay, so a over x plus bx plus c over x squared plus 1 just to the power of 1 in this case, plus dx plus e over x squared plus 1 to the power of 2, because it's only being repeated 2 times. Okay, so if you notice, a here, it's not a linear function because x is just to the power of 1, so it doesn't make sense to have a as a linear function, then it would be improper fraction. So now just try to find what are the values of a, b, c, d, e. Okay, you can skip the video if you want, but I'm just going to proceed to do the step-by-step calculation for those who needs it. So a times squared plus 1 squared plus bx plus c, this one times x, and x squared plus 1 plus dx plus e, this one times x only, equal to the numerator. Okay, so now you want to just get a system of equations, so you expand. So just look at the coefficients. So for x to the power of 4, it's 0. So a plus b, x to the cube is negative 1 equals to c, x squared is 2 equals to 2a plus b plus d, and the 1 equals to a. So now you have just got c equals to minus 1 and a equals to 1. So you want to just get the values. and actually e equal to 0 because yeah, I've got this e thing, x. Okay, just try to do that. C plus what? C plus e equals to -1. Then yeah, you get e equals to 0 because c is -1. Then e is -1 minus -1, then get 0. And you get values of b 1, c is -1, d is 1. Okay, so you just substitute these values into this fraction here. Then we can do the integration. So after substituting the value, you get the simplified version of the integration is integrate 1 over x plus minus x minus 1 over x squared plus 1 plus x over x squared plus 1 squared dx. Okay, so here this first part you can integrate easily with respect to x, and the second part you can divide them, so x over x squared plus 1 dx, and the last term. Okay, so the term here and the term here, you can have a look at the integration table to get a straightforward formula to get the integral. So you will get, if you look at the integration table, you will get this one here, like what we did before in case 3. But the last one here, you need to do a u substitution. This one, you need to do a u substitution. So let's, in this case, let u equal to x squared plus 1. Thus du equals to 2x dx. Thus x dx equal to du over 2. Thus you will get integral of 1 over u squared du over 2, and 1 over 2 integrate 1 over u squared du is 1 over 2. What do you get here? U. Okay, you get minus 1 over 2u. Then you put it back in terms of x. 1 over 2 times x squared plus 1. Then you put it back here. Okay. Times, or okay, it should be minus. Don't forget the integration constant. Okay, so that's it for case number 4.